Huygens principle says that if you have a wave front advancing, let's say this is a wave front, say waves moving through air, through water from some source over here, moving out in all directions. Each point of this surface is a source of little wavelets that move out from that point. So it's like you have a little source here and you have wavelets moving out like so. Little source here, wavelets moving out. An infinite bunch of little sources, of which I've only represented a few, obviously. Now, if these wavelets move for some time, then this wavelet will be out this far in front, this wavelet will be out this far in front, this one this far in front. And at the forefront of all these wavelets, you have a new wave formed. It's the sum of all the wavelets, and it's called the envelope of all the wavelets. You got all these little wavelets coming out, and this thing, the outer envelope of all the wavelets, is where your new wave's going to be at that time. Now let's apply this to the situation where we have a wave, plane wave this time, traveling across a medium, where we have an index of refraction N1 on this side and N2 on this side. Excuse me for blocking the view, so the only way I could get an angle to write. The direction of propagation is perpendicular to the plane wave. Now, if every point here sends out its little wavelets, then the wavelets will move some distance between here and here. This wavelet will move this distance, this wavelet will move this distance. Now what about this little wavelet here? It's moving part of its distance in this medium and part in this medium. Now if N2 is bigger than N1, which I'm implicitly assuming here, then it won't move quite as far here, and the distance from here to here won't be quite as great as the distance from here to here. And this wavelet that comes from a point that was originally at the interface moves all the way in the medium with index of refraction N2. It doesn't move nearly as far as this. This causes the envelope of the waves to take this direction here and another direction here, and it's going to turn the wave in this direction. We continue. The wave that's now here travels only little ways into the medium. These wavelets travel only little ways, whereas these wavelets still outside the medium N2 and the medium N1 travel a much greater distance. And we again see how the wave gets turned. And these waves, then these wave fronts will be closer together than these. We're assuming an equal time interval between this front and this front and this front and this front. That causes the turning. If we look at the geometry of the situation, if this is the interface, we have an angle theta 1 here of this wave front with the interface and an angle theta 2 of this wave front with the interface. In a time delta t, this wave will move distance v1 delta t from here to here, and this will move a distance v2 delta t from here to here. We can see that the sine of this angle is just v1 delta t over whatever this hypotenuse is, and the sine of this angle is v2 delta t over the same hypotenuse. So that the sine of this angle divided by the sine of this angle is just this distance divided by this distance. Again, both distances being part of triangles with the same hypotenuse. And then from the geometry of the situation, we divide out the delta t. We see that the sine of theta 1 over sine of theta 2 has to be the ratio of the velocities, which is the reciprocal ratio of the indices of refraction. And this is a derivation using Huygens' principle of wavelets and wave envelopes and wave fronts of Snell's law.